So this section is about viscoelasticity, and then I want to talk about the Newtonian versus non-Newtonian viscosity. And this section is actually not so well described in the textbook, but I think it's important. So for me, I wanted to discuss you about this concept. There is something called Newton's law of viscosity. Okay, so viscosity is zeta. And it is a relationship between stress and what they call the strain rate. And this is a time, most likely the viscosity measured under the shear. So this is a shear strain. Okay, and then they are proportional to do this. So therefore, so if you're looking at the Hookean spring elasticity, and then this is the stress is going to be proportional to the strain, okay? Because this time gamma is a shear strain, and the proportional constant is we typically call G, okay? And then this is a shear modulus. Okay, so this is the viscosity. So therefore, if you're looking at the Newton's law, what it means is if you divide it, stress divided by strain rate, and this is also known as, they just put a time derivative, so they put a derivative as a dot on the top, and this is a C, the eta. So it is a constant and independent of viscosity, shear rate. And one of the experiment people do is they have put it on the sample between two parallel plate, and they essentially rotate this at different RPM, and the shear rate is defined by the thicknesses and how much of the RPM is related to. So this is essentially rotation per minute, how fast you are rotating this, and this plot shows this is a stress. Okay, so different people use a different notation, and this is a strain rate, and they're trying to show the Newtonian's law, which is that's the Newtonian's law. So it is a constant slope, right? Constant slope. So what that means is constant viscosity. Therefore, when you do the experiment, you will see that the viscosity versus essentially strain rate, it is flat. Okay, it's a single independent of the shear rate. So that's the figure that this is what is called a Newtonian. Okay, so that's the case of the Newtonian. For the case of non-Newtonian, and then I want to show the shear thinning, and then this one actually I want to use the figure as it is. So let me try to use this. The shear thinning is you have an initially pretty high slope, and then the slope value is getting smaller and smaller and smaller, right? So your slope is not constant, slope is changing. So for that regions, that your value is going to be something looks like, in the beginning you have a little constant, and then you want to do this, okay? And then I want to just let you know, and in the rheology community, they use in the log scale, and this is a log scale just to want to show the change, how fast it's changing. And this is a non-Newtonian, and this region is called the shear thinning. Okay? So because of the when the RPM goes up, right? So this is proportional to some RPM. As you rotate it faster and faster, your viscosity is coming down. So that's a shear thinning, and the shear thinning is very common for polymer melt. There is another technique called phenomena. It is called a shear thickening, and this is quite unique. And the way that this one works is it's a low viscosity in the beginning, and the viscosity actually gets higher and higher and higher and higher. That's a shear thickening, and the shear thickness is common in colloid suspension. One famous example is actually corn starch suspension. If you put the cornstarch mixed with the water, and actually you will see that when you're stirring it, it's easier to stir at lower stirring speed, and when you're trying to stir faster, it's actually got more difficult than the lower speed, and then that's what is called shear thickening. So the shear thickening is essentially happening in this way, and in most cases actually it is combined. So sometimes they have these regions and shear thinning, and then finally they go to shear thickening. Okay, so this region is a shear thickening for the colloidal suspension. There are some cases that is unique for the what is called a Bingham plastic, and you need a stress. It would not flow. It's almost like a slope is here is infinite, and then the module almost like it doesn't flow until, and then it start to flow, right? And this is what we call in the Bingham plastic. This is one of the phenomena. This is like what they call the yield stress for this fluid-like Bingham plastic material. And other than that, this behavior is same as Newtonian, right? But the behavior is they have a certain kind of the yield stress, and I think that there's something that is a catch-up is very closer to what it is, but I am not so sure. So, so I will just leave it as a Bingham plastic is the material just looks like that. So I look at this one is actually want to give you a recap. If you put this log viscosity versus strain rate, right? There's strain rate, and Newtonian is something that does not depending on how fast and how slow you're rotating it, whereas this is a shear thinning. Viscosity is lower at high RPM, and this is actually viscosity going up, and this is what we call the shear thickening. Okay, so those are the interpretation of what people says. And I also find some a book, and this is a book by the very well-known polymer rheologist Garth Wilkes, and he's a Virginia Polytech, and he actually wrote a Journal of Chemical Education articles and with this title, and I like this because of it gives some very interesting, nice summaries about how people do the shear because of the shear rate. And this rheology is very important, and understand the viscoelasticity is very important. But one of the most important reference point is this. What is a processing? We are doing the injection molding and do a lot of processing of the polymer melt, and that shear rate is related to about this much. Okay, so that's in the log scale. Okay, so this is a log scale. So this is what that means is here is 10 to the 4th per second, 10 to the 3rd per second, 10 to the 2nd per second. That's a very fast rate. And there's a types of the rheological instrument called the capillary rheometer, and this is essentially pushing the polymer through a nodule. So the way that it works is you putting the polymer in a melt and pushing through the nodules. So there is a kind of the stages that pushing it out, and then they it is a more like a capillary. So this is a high temperature is a polymer melt, and then they push it through the die. Okay, so this is a die, and then what is a flow rate, and then they can kind of estimate the rheological properties. So this is the ranges. The capillary rheometer is very related to the processing condition. So and then this is very related to a lot of shear thinning is manifested in these ranges. Okay, and there is another ranges of the polymer rheometer that we can use, and this is what is called the rotational. Okay, rotational rheometer is essentially this is what we have in the lab. Let me do this way. And this is essentially what we call the parallel plate. So you're going to put your sample between essentially two coins. It looks like a two parallel disc, and then you're going to rotate this, and then depending on the RPM. And this one, the shear rate ranges is about here. Right? So it is you will see some portion of the shear thinning, but the ranges of the shear rate is not to the higher ranges such as from the capillary viscometer. So if you truly wanted to understand something that rheological behavior related to processing, you need to have a capillary viscometer or rheometer. And the rotational shear rheometer, and you have those ranges. And he also, I think it's also a good idea for you to develop some basic understanding. I think if you took the fluid mechanics, you probably know that water viscosity is about 1 centipoise. That's 1 millipascal second, and that's the ranges. Whereas if you look at the polymer melt, and that ranges from 100 to the million Pascal seconds. Okay, so why the viscosity has this unit, and if you remember, the stress is a viscosity times the strain rate, and this unit as a Pascal, and this unit as per second. So therefore, your viscosity has a unit of Pascal times second. Okay, so remember that's the unit of the melt viscometer. Okay, so and then I want to show you one of the shear thinning data. This is from the same paper from the Garth works, and you saw this, and this is essentially once again the viscosity and the shear rate. Okay, so then the shear rate and then is most likely the polymer looks like that, and then that's the viscosity and the shear rate. And you remember in the first day of my class, I show you the log molecular weight versus log weight average molecular weight. This is a very similar plot, and the way that when they say this molecule, the viscosity for different molecular weight of the same polymer, this molecule is essentially corresponding to what is called the Newtonian viscosity region. Okay, so as you can see that there's a flat region, right? This is always we call Newtonian viscosity, and also it's called the Newtonian region. Whereas this one is the viscosity is now depending on the shear rate, and so this is a non-Newtonian. Region. Okay, this is a Newtonian. Okay. And then what they did is they put essentially this is a Newtonian viscosity. Sometimes they call it zero shear, but that means zero shear rate, okay, viscosity. And that's the value that they put it in, and what they find out is the slope here is 3.4. That's why the Newtonian viscosity, and sometimes that's why they, to distinguish, they put a little like a knot there, and that's in the limit of your shear rate goes to 0. So in the limit of your viscosity, when your shear rate goes to 0, and that's the Newtonian viscosity, and that one is the one. So the correct notation will be this. Put a subscript, and then that's 3.4 when entangled state. And this breakover happens at the molecular weight is about 2 times entanglement molecular weight. And there are 2 examples that this paper introduced, and I think that I want you to know. And the first, nonlinear rheological effect. And the first one is called the die swell, and this is very common in the fiber spinning. So this is a polymer melt, right? You have this polymer melt, you're kind of pushing through the nozzle. When they're pushing through the nozzle, what do they have is, you see these chains are more stretched. So the chains are elongated. Just like this, right? The chains are more elongated, and they have a force to kind of expand the other way when those constraints through the nozzle is removed. And so that's why you are seeing this kind of the new form, which is now chains are more expanded when they come out through the dies. Right? And then what you can do is, okay, so then I know that is a diameter of that is essentially from the die diameter, right? And then you can measure the fiber diameter, and then this is a swelling ratio. So the fiber diameter divided by d naught, which is the original die diameter, that is a swelling ratio. And so you design your dies, and this is a die diameter. And that design is not going to be your fibers diameter, because of when they come out, these polymers start to kind of like this, right? So they want to kind of go the other way. So that's why in the beginning it was like this, and then later it will be much thicker in that regions. So that's one way that when the polymer chains essentially more like a spring. They want to have more like a Gaussian coil, but when they are stretched due to the processing condition, and those constraints are relieved, and then they want to have a molecular motion, and that we can see it as a die swelling in the first cases. The second one is a Weisenberg effect, and there is a rod climbing effect, and you can see if you go to if you search for the YouTube videos and Weisenberg effect, there's some people who show this. So this is you put in a melt or the entangle. This is essentially entangled melt or polymer solution. If you do that, and due to the centrifugal force, if it is a Newtonian, just like water or Newtonian fluid, if you do this, the centrifugal force, you have a meniscus climb up this way. Right? But if you entangle fluid, and then the polymer chains are kind of entangled and they form, and it's climbing through the x-axis that is on the rotation. So and so this is what's called the road climbing effect, and what the Heisenberg effect. And those are the two things that is quite distinct from the Newtonian fluid. And this is essentially non-Newtonian. Okay. The molecular perspective of this shear thinning is also the chains are more like a stretched. Whereas this in the Newtonian regions, and the chains are more taking its own Gaussian form, and this one is more like a stretched chain because of higher strain rate. So their chains are more like a stretched. So they can slide each other easily, so the viscosity, apparent viscosity, is low, and that's a good thing. The lower viscosity means it takes less energy to move the polymer melts around, and that's quite important and desirable actually in the field of polymer processing.